Hi. I'm gonna give a few minutes for more people to join. But while I'm waiting, feel free to let me know in the little chat thing what exam boards you guys are. Today's session is gonna go over like all of them, basically. Mm. And where I can, I have tried to highlight the things that are different between the different exam boards and the places where there are differences. Um, But the differences are quite minimal, to be honest. And the kind of aim of what I'm trying to give you guys today is more to understand what's actually going on in the transition metal topic rather than like hold your hand through every single example that you're going to see. I'm trying to get you to kind of understand the chemistry that links everything together and enables you to sort of get the bigger picture. Okay, OCRAs, AQAs. I like OCRs, my favorite, OCRA. AQA is all right as well. I actually prefer this topic in AQA, but in general, I prefer OCR for just like the way that they approach things and the way that they mark things. Cool. Also, as it is a big topic, I'm not sure if we'll have time to go through questions today. Hopefully, we do. Um, but I'm going to try and get you through all of the actual material so that you can understand what it is that's meant to be understood. Um, I'll wait until like 5 past before I actually start. Yeah, I'm going to send you guys a recording of this after. Um, and I might put it like on YouTube so other people can watch it if they want to. Also, with regards to participation, guys, um, you can write some questions in the chat. I can't lie, I'm very easily distracted, so I'm going to try as much as I can to just get through what I've got to get through and come to the questions maybe at the end. But if there's a question about something I'm literally talking about, then feel free to talk about them. You can also interrupt me with your mic if you're brave. If you're not shy, go ahead. Um, mm, 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 mm. But yeah, as you guys have all got here from my TikTok, and if you've watched enough of my videos, you'll realize that I'm always basically banging on about the fact that you're meant to understand chemistry and not memorize it. And I can say, as a student, I didn't understand it, not really properly. I was just kind of memorizing things and panicking about it being in my exam. But actually, it's not that difficult if you just think about it. The whole thing like makes sense as one big picture, and it all comes back down to like positive and negative and opposites attracting and like atomic structure and that kind of thing. So, where possible, we're going to try and think about things on like a really, really fundamental level. And as I said, I'm trying to get you through the actual chemistry that you're supposed to understand in this topic. Also, with a focus on one of the good things about the transition metal topic is the fact that most of the stuff that you learn about in this topic, you've actually learned about in other places. Um, and it's just a case of applying it to transition elements. Also, I somehow attached this document to the Zoom meeting, so you should be able to download this. I think I can also like put it in the chat. So if you want a copy of it, you can have a copy of it. Let's see if I can do that. I'm literally an old woman, you lot, and I'm all like with technology because obviously I'm old. Speak. Um, There you go. So you lot all have a copy of this little slideshow that I made yesterday. Um, yeah, all right, I'm gonna get started. It's 5 past. If you have questions, as I said, let me open the little chat thing so I can actually see if you lot are talking to me. And then I'll get started. So basically, I made like a little slideshow summarizing all of the things that you guys are going to need to know about for this topic, and I'm going to go through the little slideshow with you lot now. And yeah, talk you through everything that you're supposed to understand. As I said, with a main focus on trying to link it back to other places that you've seen this chemistry, but just maybe not applied to transition metals. So the first thing that you really need to know about transition metals is the definition of a transition metal. So the definition of a transition metal is a D block element that forms at least one stable ion with a partially filled D subshell. So one of the most important things, or yeah, most important things to understanding here is going back and thinking about long, long, long time ago in first year when you learnt about electronic structure and the rules for filling up the different like orbitals. You would have remembered that the 4s orbital fills before the 3d orbital. So when you look at the electron configurations, they're following that rule. However, there are two exceptions, but these two exceptions follow another sort of rule that you've seen in other place, which is that having an orbital that is completely filled or half filled kind of is like extra stable. So if you look at the electron configurations for the different transition metals. Titanium and vanadium are kind of as expected. So 4s2, 3d2, 4s2, 3d4. You would expect, sorry, 3d3. You would expect 4s2, 3d4 for chromium, but instead you get 4s1, 3d5. That way, both of the orbitals are half filled and it gives it like extra stability. Then we go back to the usual filling up the 4s. So you've got 4s2, 3d5, 4, manganese, iron, cobalt, nickel, and then copper, you would expect 4s2, 3d9, but instead you get 4s1, 3d10. So you've got one full, one half filled, extra stable. So electron configuration is pretty straightforward. The 4s orbital also empties before the 3D when forming ions. A lot of the time in exam questions, they ask you for electron configuration of transition metal ions. I would always recommend working out the electron configuration of the atom when it's neutral first, and then working out what it is as an ion, just because sometimes if it's one of these exceptions, you might miss that and then get it wrong, and you don't want to do that. Other little thing to note, scandium and zinc. Scandium is the first D block element on period 3, zinc is the last. These two do not count as transition elements because even though they're in the D block, they do not have stable ions with partially filled D subshells. Scandium's only stable ion, scandium 3 plus, has an empty D subshell, and zinc's only stable ion, zinc 2 plus, has a full D subshell. So these two don't count as transition metals. Then next thing we're going to look at is properties of transition metals, physical properties as well as chemical properties. The physical properties are things that you should already know about and be able to explain and understand using like prior chemistry knowledge. The chemical properties of transition metals is what we're going to learn about basically throughout the rest of this session today. So physical properties, I always think about transition metals as quote unquote normal metals. So iron, copper, gold, silver. Physical properties of these, you know, relate to metallic bonding. So um, lattice, regular arranged, positive ions, sea of delocalized electrons, layers that can slide, malleable, ductile, good conductors, delocalized electrons, high melting and boiling points, strong interaction between the ions and the sea of delocalized electrons. So this is all stuff, prior knowledge. A lot of that's even GCSE. Chemical properties of transition metals. I'm going to just list them now, but these are the things that we're basically going to look at for the rest of this session. So first one is the fact that they form complexes or complex ions with ligands. They form colored compounds. This is one of the things that's kind of different between the different exam boards. I believe OCRA, you guys don't learn as much detail about how they form the colors as EdXLs and AQAs do, but I'm going to go through it. It's not really that difficult and it doesn't take long, so everyone just learn that today. Then we'll look at variable oxidation states, which is basically redox part 2, which again is not something that's like completely new to you guys. Catalytic activity is basically explained by variable oxidation states as well. So yeah, the underlying reason for their chemical properties is because of their partially filled D subshells. And a big part of it is also to do with the fact that the 3D and 4s orbitals are very close in energy, hence why there's like a swapping in the order kind of thing. So normally when you're making a metal ion, like if you're making, I don't know, Mg2 plus, you make Mg2 plus, but you can't really make Mg3 plus because the next electron's on an inner shell and it's really difficult to remove. For transition metals, you can remove the outside four S's and then you can start removing 3Ds as well because the orbital's really, really close in energy. So this is why your transition metals will have variable oxidation states. So instead of just having one stable ion, you'll have multiple stable ions for each different metal. All right, cool. Next part, complexes. This first bit, you're going to learn a lot of definitions, but the definitions, again, whenever it comes to definitions in chemistry, you always have like in the book, there'll be like a fancy sentence that you're supposed to memorize. And if you say that, you get full marks automatically in the mark team or whatever. And so naturally, students tend to just try and memorize these sentences. No, I don't like, I don't memorize the sentences. You're not supposed to memorize the sentences. What I want you guys to try and do is understand the physical process that they're talking about, understand what's actually happening. If you can then describe that with appropriate chemical language, you've got that perfect word definition. So try and think about what we're actually talking about here rather than just trying to memorize the sentences. So first and like definition you're going to get is the definition of this complex ion. So a complex ion is when you've got a transition metal ion that is surrounded by coordinately bonded ligands. You guys already know what a coordinate bond is, or dative covalent bond. That's when both of the electrons are coming from one thing instead of one each being shared. Um, because the transition metal complex has got coordinate bonded ligands, the definition of ligand is kind of like the reverse of that. So a ligand is something that forms these coordinate or dative bonds with transition metal ions. Therefore, by definition, must have at least one lone pair of electrons because it needs to have that pair to donate in the dative covalent bond. We then have monodentate, bidentate, and multidentate. One of the other things that maybe this is just me being like super neaky, but when you look at a lot of the words that come up in chemistry, they have like their roots in Latin and Greek, and you can break them down into little pieces, and then the little pieces of the word generally tell you what the thing is. Even the ones that are in English, to be fair, if you actually think about like the terminology that's being used, it usually describes what's actually happening. So again, don't just like blankly try to memorize these phrases, but think about like, why did they call it that? What relation does the name have to the thing it's describing? And normally it's like very does what it says on the tin. So for mono, bi, and multidentate, I'm sure we all know mono means one, bi means two, multi is multiple. The dentate part is like dent for dental, meaning teeth. So monodentate have like one set of teeth, you could imagine, which means that they've got one atom with that lone pair that can form the coordinate bond, whereas bidentate ligands have got two sets of teeth. So there's two places where they can like form a bond or like bite and attach to the metal ion. Multidentates have got more than two. Some common examples that you'll see, we've got ethane diamine. So that's just literally two carbons with NH2 on either side and then hydrogens on the rest. The two nitrogens in the amine groups have got lone pairs on them, so they can form dative covalent bonds with metal ions. Another common example, ethane dioate. So that's where you've got two carbons. Each carbon has got double bond O and then O minus. So it's C2O4 2 minus is the formula of the ion, and then the O minuses can form dative bonds with metal ions. Last one is EDTA. This is a hexadentate ligand, so it forms six coordinate bonds with the metal ion. And you don't need to know how to draw the whole structure of this. They'll show it if you need it. But you do need to recognize the atoms that form the dative bonds. So it's obviously the nitrogens with the lone pairs and the O minuses. EDTA's got four O minuses, so it's EDTA 4 minus and then two nitrogens that's got the lone pairs that can bond. And these are the most common multidentate ligands that you'll see coming up with different transition metal complexes. Then a little bit over here is talking about, sorry, my little chat box is in the way. Another sort of two definitions or two things that you need to be aware of when you're looking at complexes is the overall charge or overall oxidation state of the complex. And then oftentimes you'll have to use that to figure out what the oxidation state or charge is on the metal ion. So I put an example here, it's quite a simple one. Cobalt chloride, COCl4, 2 minus. We know that chloride ligands are -1 and there's four of them. So the chloride is taking us down to -4, but the whole ion is -2. So in order to get from -4 to -2, I'd have to add 2, which means that my cobalt ion must be a cobalt 2 plus. So sometimes you'd see different ligands and different ions sort of combined, and you'd have to figure out which charge your ion has based on the ligands instead. Common ligands and their charges, you've seen these ones. So ethane diamine, which is neutral, ethane dioate, which is 4 minus, C2O4, no, sorry, 2 minus. EDTA is 4 minus, water neutral, ammonia neutral, cyanide -1, halides -1. So most of them are molecules and things you've seen before, but this time they're just using their lone pairs to behave as ligands. Then next things we're going to look at are the shapes of the different complex ions. This is not difficult. You already know about shapes of molecules. The main thing to understand here is the reason why certain things have got certain shapes is all to do with really the size of the ligand. So if your ligands are small, you can fit 6 of them around the metal ion and you'll have something octahedral. So that would be for ligands like water or ammonia, which are quite small. Larger ligands like chloride you wouldn't be able to fit 6 of them around one metal, so you end up with tetrahedral shape instead. It's all pretty straightforward. Sometimes you get square planar when it's something is 4 coordinate. The coordination number, sorry, I skipped my little definition up here, is the number of dative bonds that are made with the metal, not the number of ligands attached to it. So even though this has got 1 ligand, it's still 6 coordinate. But yeah, you can also get 4 coordinate square planar. This is normally nickel and platinum, and then 2 coordinate for silver, so just be linear. But the sort of main things that you're going to see changing and reaction wise is going to be going between octahedral and tetrahedral, and reason being size of ligands. Then a little bit about isomerism. Again, you guys already know about isomers. This is nothing new. You can have geometric isomerism, cis-trans, in transition metal complexes if you've got ligands of more than one type. So in this example, I've got water and ammonia. Here, the waters are opposite each other and they've got 180 degrees separating them. So this would be the trans isomer. And then here, they're next to each other with 90 degrees. So this would be cis. And you can do the same cis-trans isomerism for the square planar complexes as well. So you can see the version I've drawn here is a cis version because the 2 chlorines are cis. If I'd put one of the chlorines down here instead, I'd have the trans isomer. But not rocket science. You've seen this before. This is nothing new. The other type of isomerism you can get is optical. Again, you've met this before. In this instance, though, instead of looking for chiral carbons, where you're looking for the carbon that's got 4 different things, you're looking for octahedral complexes that have got bidentate ligands. If you have an octahedral complex with a bidentate ligand, it would exhibit optical isomerism. This one can be a little bit difficult to kind of visualize, but I'll try and explain it. Bear with me if you can. It all comes down to understanding the meaning of these like dashed bonds and the like thick triangle wedge bonds. The wedge bonds mean coming out of the paper towards you. The dashed ones mean going into the paper away from you. So if you think about what this kind of looks like in 3 dimensions, this loop is actually like flat in the plane of the paper, like this. Well, I can't draw it in 3D, it's ridiculous, but it's flat. Then the loop at the top is sticking backwards and the loop at the bottom is sticking forwards. So if I was to then take this version, the mirror image, flip it around, I would be able to make these 2 bits line up, but then the bit at the top that's meant to be going back would be coming forwards, and the bit at the bottom that's meant to be going forwards would be going back. So it would never superimpose. So we've got optical isomerism here. But again, this only happens when you've got octahedrals with bidentate ligands. If they're monodentate, this is not an issue. Hmm. Then we get to the formation of colored complexes. This is the bit that, as I said, in OCR, you kind of just need to know that they're colored. I don't think you need to know as much information as to why they're colored. Um, Check in your specification. Obviously, my word is not actual like law, but I'm pretty sure when I went through you guys' book yesterday, they didn't have this bit in there. But it's not difficult to understand. So even if you're in OCR, you might as well listen. um, the formation of colored complexes. Whenever people ask me about this, this diagram basically just pops up in my head. So I thought I'd paste it here and explain the diagram for you, to explain why the like this. If you can explain this diagram, you get it basically. So the first part of the picture shows the 3D orbitals. In this example, they've used a nickel 2 plus ion, and it says this is the ion without any ligands. So this is when nothing is forming those dative bonds with the ligands. And if you look, they've put like a y-axis saying the energy is going in the upwards direction. And at the beginning, when there's no energy, all of these boxes, sorry, when there's no ligands, all of these boxes are on the same line and they've all got the same amount of energy. So we can say that the orbitals are degenerate. They've all got the same amount of energy. Then, if you introduce ligands, you can see that that changes, and some of the orbitals go up to higher energies, and some of the orbitals go down to lower energies. And now we have an energy gap between the ground and excited states of the 3D orbitals. And it just so happens that this energy gap is the same size as electromagnetic radiation in the visible light region of the electromagnetic spectrum. So, when visible light encounters things, metal ions with ligands and a split in their energy levels, the certain frequencies slash colors of the light get absorbed, and then the energy that they absorb promotes electrons from the ground state up to the excited state. So the electrons basically take in energy or different colors of light and use it to jump up to the excited state. The size of the energy gap determines obviously which frequencies slash wavelengths slash colors of light are absorbed. And the colors of light that get absorbed are the opposite of what we see, because we get to see everything that's left that doesn't get sucked up by the electrons. Hopefully that will kind of make sense to you guys. So if you look at the diagram, you can see the electron starts down here, then it absorbs some light energy and jumps up to the excited state. If you remember, I don't know if like doing art in lower school, if you ever drew a color wheel, I'm going to draw one for you now. It's going to be really horrible. It's like this. And you have like your primary colors and like, like this. And then in between each color, you put the color that it would make if you mix them together. I'm sure you guys must remember this. Like that. Colors that are opposite each other in the color wheel are known as complementary colors. So this, when you like when the transition metals are absorbing frequencies or colors of light, what you end up seeing is what's opposite to what's been absorbed. So if I absorbed all of the red light, I would end up seeing green. If I absorbed all of the blue, I'd end up seeing orange. If I absorbed the purple, I'll see yellow, and so on and so on. So you can say that the colors that are observed are the complement of the frequencies that have been absorbed. The way that we relate the energy gap to frequencies, wavelengths of electromagnetic radiation is using this equation down here. There's two versions of it. So delta E, the energy gap, and this is going to be expressed in joules, or like the size of the energy gap is going to be in joules, is equal to hv or h nu. H is Planck's constant. It's just a constant that you'll get given value for in your data book. And then V is the frequency of light in hertz. Or another version you can have is hc over lambda, because c over lambda is equal to v, basically. So depending on which values you get given in the question, you can use either version of this equation. With all equation questions and all calculations in general in chemistry, by this point, hopefully you should be in the habit of thinking about and looking at units. So I'm not going to spend ages going over like examples and stuff. You're big enough now. Rearrange it, check the units, plug in the numbers. It's the same old situation. With regards to the theoretical side of things and how this is going to link to equations, in the topic of transition metals, there are only three types of reaction that ever happen, like literally ever. It's either going to be redox, where it's changing oxidation state. It could be a ligand substitution, where you change the ligands, or it's a precipitation reaction. So we're going to look at those as we carry on going through. And oftentimes, the sort of difficult questions in the transition metal topic is figuring out what reactions happened, sometimes by looking at a change in color. So understanding how this all ties in, we've just said the reason that they have different colors is because the energy gap is a different, like different sizes, and different size energy gaps absorb different frequencies or different colors of light. So anything that therefore changes the size of the energy gap is going to change the color. And we know that the energy gap was only there when you introduce a ligand. So it kind of explains why certain changes will produce different energy gaps. So if you have different oxidation state of the same metal, different energy gap, different color. If you have different ligands, different energy gap, different color, different coordination number, different energy gap, different color. And you can see some examples down here. So like iron 2 is green, iron 3 is brown, cobalt with water is pink, but cobalt with ammonia is straw colored. Copper with water is, or sorry, well, more importantly, copper octahedral blue, copper tetrahedral yellow, but different ligand as well. So when you're looking at reactions, these are the sort of changes that you're going to see, and they're going to expect you to notice when these things have happened. I've made this little table, I made this a couple years ago actually, which is a summary of the colors of the different ions in aqueous solution. I said AQA, no titanium. Apparently, you guys don't need to know this. Again, check your own books, check your own specification, make sure you know everything that you're supposed to know. This is general overview so that you understand what's happening. But a lot of the questions and a lot of the reason why I think people find this topic difficult is because you're expected to like memorize most of these. However, a lot of them you actually know already from other parts of the course. So I'm just going to quickly show you some of the ones that you probably have encountered before that will help hopefully make things a bit easier. So this orange to green with potassium dichromate oxidizing alcohols, you already know that color change. The purple to pink manganese you might have seen in some titration calculations and like redoxy things before. I feel like by this time everyone knows that Fe2 plus is green. Yellowy brown for Fe3 plus. Think about rust. That's kind of cool. Blue for copper sulfate. I feel like everyone knows that by now. So it's not as bad as it looks. You do have to remember the vanadium colors, but you can make up a mnemonic or do something to help you memorize them. But don't be intimidated by the colors. And I think my piece of general advice when you're doing chemistry and you're trying to get your A level, when you are practicing and you're not in an exam or in a mock or whatever at school, if you don't know something, just go and find it out. There's no point doing like exam questions in exam conditions at home if you don't know the answers to stuff, because then you're just going to guess and get it wrong. So what I would advise is just do practice questions, and then if it asks you for the color of something and you're not sure, just go and look it up and then write it down. And then if you do loads of questions and you write down Fe2 plus is green enough times, you're going to remember it. So don't put yourself in a position where you're like being tested and doing everything off by heart, with like no books and under timed conditions when you don't actually know what you're doing. That's for when you've mastered it. But while you're still learning, the most important thing is that you understand what's happening and that you can make sense of why things go on the way that they do. So don't turn it into a test until it needs to be. When you're doing questions on this topic, open your book, have the table of colors with you as you're going through them. All right, cool. Then we're going to start looking at the reactions, different types of reactions. As I said, there's only three types of reactions that you're really going to see. First one we're going to look at is ligand substitution. The important bits to understand here, I've written in black. And then there's different examples underneath. This is another place where exam board to exam board, it does differ a little bit. Some of you guys might learn different examples to exhibit the same principle, to sort of demonstrate the same principle. So the principle's in black, but look in your book again to see if there's any other specific examples you're supposed to know about. So the first kind of rule, or the first thing that you need to understand, is if you swap a ligand for another ligand of similar size, it will keep the same coordination number. That makes sense because we know the coordination number is determined by size. So if you start with the example here, cobalt with 6 waters, and you swap the 6 waters for 6 ammonias, it stays as octahedron 6 coordinate because both of the ligands are small. However, if you swap the ligands for a ligand of a different size, then you might get a change in coordination number. So the three examples here, we started off with octahedral 6 coordinate complexes, swapped the octahedral 6 coordinate complexes for tetrahedral 4 coordinate because we added large Cl minus ligands, and you can't fit 6 of them around the metal ion. The other little rules that we've got says ligand substitutions are easily reversed unless the new complex is much more stable than the old one. The two reasons why that might happen is either the ligand forms a much, much stronger bond with the metal. So the example we have here is iron 2 plus with 6 water ligands being swapped for 6 cyanide ligands. The bond that cyanide forms with iron is much stronger than the bond that water forms with iron. And so once that reaction happens, it's very difficult to send it back in the other direction, whereas the ones above would be a bit easier to send back in the other direction. This also links into hemoglobin and carbon monoxide poisoning. Hemoglobin is a complex ion with iron, heme, globin, and water or oxygen. Carbon monoxide comes along, bonds to the hemoglobin really, really strongly, can't unbond it, and now your hemoglobin can't do its job and it's poisonous. So they'll probably write about that in your book. Like if you, there'll be, you know, them little boxes where it's like, links to whatever. So yeah, you'll learn about that somewhere. The other reason why you might get a reaction that can't reverse. Oh, hold on. Can I upload this? I will upload to YouTube. How would you know if ligand is small or big? Periodic table. Just literally, the answers to every question is the periodic table. So it's not a stupid question, that's a wonderful question. But that demonstrates what I was saying right at the beginning about like just trying to visualize and picture like physically what is actually happening here. So if you look at the periodic table and compare, for example, let's think about ammonia versus chloride. Nitrogen is period 2. Yeah, nitrogen's period 2, hydrogen's period 1. So NH3 is going to be small. It's going to be the 3 hydrogens that are 1s orbitals, and then the nitrogen that's got a 1s, a 2s, and some 2p, and that's it. Chlorine, period 3. So it's going to be much bigger. It's got 1s, 2s, 2p, 3s, 3p. So it's much, much larger in size. Like practically everything that you're ever supposed to understand in chemistry, if you keep asking why and like dig back far enough, it links back to atomic structure or like molecular structure or bonding or intermolecular forces or like it's a physical thing. Atoms are physical, real things that are actually moving around and interacting. So try and bring it back to that as much as possible. All right. Yeah, I was gonna say the other reason why you might get an irreversible ligand substitution reaction is to do with entropy. So the example that we've got here, you can see that we're swapping 6 ammonia ligands, which are monodentate, for 3 ethane diamine ligands, which are bidentate. So what we're going to end up doing is, as you can see, we're starting with 4 particles, so complex 3 bidentate ligands, and ending up with 7 particles, complex, and 6 waters that we've kicked off. So in terms of number of particles we've increased, that increases our entropy. And if you want to think about enthalpy for a second as well, the enthalpy change here is almost zero because we're breaking six nickel nitrogen bonds to get the ammonia off and then making six nickel nitrogen bonds between the diamine and the nickel. So entropy change is going to be really, really minimal, but entropy will be large and positive. So once that's happened, it's going to be very stable on that side and it's going to be difficult to send it back in the other direction. All right, cool. Mm, 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 mm. Then we look at variable oxidation states. I was like literally laughing to myself when I was looking at these notes that I made, this little slideshow thing that I made yesterday, because I've literally written like nothing on the slides about variable oxidation states because there's nothing new here. It's just redox. You guys already know about redox. You already understand oil rig. You've already, well, you might not have, but by the time you finish all of the content, depends on the order your teachers have taught you in. But you already understand oil rig and redox. You already understand about like reduction potentials or electrode potentials and the electrochemical series. You've already done like titrations, you already know about amount of substance. None of this is really that difficult. Um, it's just applying that to this new set of molecules, this new set of chemicals that are the transition metals and transition metal complexes. But in terms of actual, like, what do you need to understand? There's not really that much new stuff here. So I'm gonna read through my bullet point. I can't even remember what I wrote on here. Right, we already know this. 4s and 3d orbitals have got similar energy. You learned this when you learned about electron configurations and you learned that the 4s fills before the 3d. So this is not difficult. Electrons can be lost from both, obviously, because they've got similar energies. That means we get different oxidation states. We've explained that before. Examples. Mm, copper 2 plus and copper 2, copper, iron 2 plus and iron 3 plus, copper plus and copper 2 plus, Mn2 plus, Mn7 plus. Different oxidation states of the same metal because you can remove electrons from 4s or 3d. And then for some reason, I thought it was necessary to put the colors of the vanadium ions here again. The reason I put that there was to remind myself that they love talking about these in questions. And realistically, it's just a case of applying your knowledge of reduction potentials to redox systems that have got transition metals in them. The same rules still apply. So whichever one is the most positive has got the more potential to be reduced and it will go forwards in the reduction direction. Whichever one's less positive is going to go backwards in the oxidation direction. None of this is difficult. You already know that when you're combining half equations to make a full redox equation, you need to balance the number of electrons. So look at the equations, balance the number of electrons. You already know how to add H pluses and H2Os and OH minuses to your redox equations to balance out like the extra bits. You've learned about this ages ago in Redox 1 and probably Redox 2, depending on how your exam board moves things around. So there is not really anything new here. Other things that kind of are a bit different, maybe redox titrations. Again, balance the number of electrons, combining two half equations to get a full equation. Not that difficult. Um, Self-indicating redox titrations are a lot of the time because the different ions have got different colors. So sometimes they'll be like, "Ooh, how come you didn't have to add an indicator because it indicates itself?" Not that difficult. Thing to look out for when you are doing questions relating to like reduction potentials, redox, vanadium, these different transition metal systems, sometimes there will be a question and they would ask about something like, oh, how can you, you know, oxidize vanadium 2 to vanadium 3? And they would have some sort of oxidizing agent that would that would oxidize vanadium 2 to vanadium 3. But then you have to realize by looking at the table and looking at the values that that oxidizing agent could also oxidize vanadium 3 to vanadium 4 and maybe vanadium 4 to vanadium 5 or maybe not. So you'd have to determine where's it going to stop, what color is it going to be at the end, what colors changes would it go through before it gets to the end of that whole process. But in terms of understanding, not very difficult, nothing new that you shouldn't have already got your head round in other parts of the course. Um, so this again, I don't know why I put this. And literally, look, I don't know why I've done this again. Um, this stuff you should already know. Redox, how to write half equations, how to combine half equations. I just put some bullet points of the usual steps that I use, and I'll do like an example to show you what I'm actually talking about. Let's do one of the orange to green. So we know that if I'm going to write a half equation for the, what is it, reduction of Cr2O7 2 minus to Cr3 plus. So this is the orange thing, this is the green thing. The steps I always take whenever I'm writing any kind of half equation are always the same. First thing, if you've got them, look at the redox potentials to figure out what's going forwards, what's going backwards, or what's being oxidized, what's being reduced. And then when you're trying to write the half equation, I always write out the sort of starting material and end material. And then the first thing I do is figure out the oxidation state of everything or like the charge. So in the dichromate ion, we've got -7, sorry, 7 times by -2, which is going to get us to -14. And then we know that we want to end at -2. So the chromium must be +6. And then over here it's +3. So I know that if I've got two chromiums that are starting at +6 and ending at +3, they both need to take on 3 electrons each. So I have to add a total of 6 electrons over here. Then I want to, as you can see, I've said like clean up the extra things that are floating around with either H plus and water if it's acidic conditions, or OH minus and water if we're in basic conditions. This normally happens in acidic conditions. So what I'm going to think is, oh look, I've got 7 oxygens that are in their 2 minus oxidation state on this side of the equation, but I've got no oxygens in their 2 minus oxidation state on the other side. What can I turn these oxygens into that's still in its 2 minus oxidation state so it hasn't done any redox? I know I'm going to turn it into water because in water, the oxygen is in its 2 minus oxidation state. So I'm going to say, let's put 7 H2Os over here. That balances out my oxygen. Then, oh no, I've added 14 H pluses on this side. It's not balanced. Let's put them over here as well. So acidic conditions. If you were going to do it in basic conditions, you would do, oh no, look, I've got 7 oxygens over here and no oxygens over there. I know I can combine my oxygens with water and turn them into OH minuses. So you've got the option to kind of go either way and sort of get rid of stuff that needs to be gotten rid of, if that makes sense. We have a question. How do I know if it's acidic or basic conditions? Um, they will tell you in the question the majority of the time, or on the table. You know, on the table where it's got like the electrode potentials, reduction potentials, it will tell you like it will say comma H plus or comma OH minus, or they'll tell you in the question that it's acidic or basic conditions. Why did I add 6 electrons? Because I started off with 2 chromiums in their +6 oxidation state and ended up with 2 chromiums in their +3. In order to get from +6 to +3, you need to gain 3 electrons, but there's 2 of them that were both gaining 3 electrons each, so 6 altogether. Hopefully that makes sense. Okay, cool. So yeah, with the transition metals and the way that it links to redox and titrations and equations, it is literally using the knowledge of redox that you already have, but just apply it to these molecules. So I didn't want to put too much time here. Things I do want to point out to you, that make the thing that makes these questions difficult, I'll be real, it's not really the chemistry, like the equation side of things. A lot of the time, these are the questions where you get them long back titrations and there's like loads and loads of steps that the student has done. And you're expected to use all of that information to go back and find, like, I don't know, the percentage of iron in an iron tablet or something like that. With those questions, the difficulty more is in the problem solving and making sure that you keep on top of all of the individual little steps and all of the things that happened so that you can basically track your moles back through all of the calculations and the dilutions and the samples and X, Y, and Z. Just take your time, like don't rush it. Make sure that you, again, I'm going to come up with one of my like top tips. When you're doing calculation questions and trying to figure out things like this, don't pick up your calculator and start putting things in there unless you know what you're actually doing. I don't normally calculate anything until I have a complete clear picture, start to finish, of how I'm going to get to the answer. I'm not going to just start whacking in numbers and hoping for the best, or just calculating, oh, I'm just going to find the moles of this, and then what? What are you going to do with that? Don't start until you know where you're going. So stick with the question. Oh, sorry, guys. Read it for a little bit, think about it, try and understand every bit of information. Why did they tell me that? If I calculate this, how does that get me closer to the answer? A big part of this, especially with the back titrations, is working backwards. But even other questions, like, if you ask me, ooh, calculate the enthalpy change of this reaction, I know that enthalpy change is equal to minus Q divided by N, and I know that Q is equal to MC delta T. So if I've got values of MC and delta T, I can find Q, and then I can take the Q and minus it, and do you know what I mean? So think about the strategy of what you're doing rather than just jumping in and calculating. And that will help you to make sure that you're doing the right thing and to understand what you're doing. But we're moving on. Catalysis, next part. This again is another bit where there is some variation, exam board to exam board. And the variation is just the examples that you learn about. So some of you guys would learn different examples of different transition metal catalysts working in different processes. And also, some of you guys learn about homogeneous and heterogeneous catalysis in a bit more detail than the others, but I can't remember who's who, so I'm just going to teach you all. Um, when it comes to transition metals as catalysts, you might remember right at the beginning, it was one of the properties, and I said, oh, this is easy because it's just explained by the fact that they've got variable oxidation states. So it's kind of like 1 point. So as we said, transition metals are happy to exist as multiple different ions with multiple different oxidation states. And for that reason, they're very good at catalyzing reactions. And the reactions that they catalyze are always redox reactions. So I'm gonna do let's do this one. That's a bit boring. No, I'm gonna make one up to try and demonstrate what's actually happening. So, right, in the reaction that is being catalyzed by a transition metal, there's always going to be one thing that gets oxidized and one thing that gets reduced. So let's imagine that we've got A plus B, and when they react together, we end up with A minus and B plus. So we can see the A has been reduced and the B has been oxidized. What the transition metal is going to do, and the reason that the transition metal is going to catalyze this so well, is because the transition metal can easily flip-flop between different oxidation states. So let's say, for example, I was going to use an Fe2 plus catalyst. I know that Fe2 plus is chilling as Fe2 plus, but it doesn't mind being Fe3 plus either. So it could give away an electron quite easily and be calm with it. So what I would do is I'll be, okay, which thing, A or B, wants to gain an electron? Oh, A does. So I'd react Fe2 plus with A to get Fe3 plus and A minus. And then, oh, B wants to get rid of an electron. So the Fe3 plus could react with the B to reform the Fe2 plus, and now I get my B plus as well. So all of the different examples that you guys are going to see, different exam boards, different reactions, different processes, different catalysts, they're all working via this same process. The reaction itself is a redox, and the transition metal catalyst facilitates that because it can pair up with the thing that wants to be reduced and the transition metal will get oxidized. Then it can pair up with the thing that wants to get oxidized and it will get reduced. And then it flip-flops between the different oxidation states. So if we have a look at what example, I don't even know what examples I put on here. Contact process with vanadium. yeah, you can see the vanadium gets reduced when the SO2 gets oxidized, and then it gets reduced to V2O4, but then the V2O4 gets oxidized back to V2O5 while the other thing gets reduced. So it's always doing this same kind of pattern. Another example here, this one's really popular. They always ask, oh, how come this reaction is slow if you don't catalyze it? It's because it's a reaction between two negative ions. But in this reaction, you can see it's doing the thing with the Fe2 plus that I did in kind of in my example. So you've got iodine that's being oxidized, sorry, iodide ions that are being oxidized to iodine, and then thiosulfates that are, is that even thios? I don't even know what that is. I think so. That thing that's getting reduced. So you can see that the thing that wants to get reduced links up with the Fe2 plus. So the Fe2 plus gets oxidized, that thing gets reduced. Then the Fe3 plus that was made can then get reduced while the other thing gets oxidized. So understanding not that difficult. There are loads of different examples. I'll be real, I can't remember the examples for this, but if you give me a question, I'll get it right because I'll just look at it and work it out and think about what I've just explained to you guys. That the transition metal is facilitating the redox that's happening in the overall equation. So go back into your actual book, look at the examples that you're given for your particular exam board and think about it in that way, and it will make sense and it won't be very difficult. And all you're doing again is, thinking about half equations, how many electrons, balancing electrons, sticking your equations together. It's all pretty straightforward. Then, for some of you guys, this is kind of important. Some of you guys don't learn about it, but I'm going to go through it quickly. The difference between heterogeneous and homogeneous catalysis or catalysts. Um, I think you all encounter the terminology, but some of you aren't expected to know like the mechanism of action. Again, I can't remember who is and who isn't, so just look it up in your own specification and check whether or not you're supposed to know it. So for heterogeneous catalysts, hetero, as we know, means like opposite, different. So heterogeneous catalyst is when the catalyst is in a different physical state to the reagents. So most common examples, like in the Haber process, reagents are gas, catalyst is a solid. Hmm. The way that heterogeneous catalysis works is that the catalyst, the solid, is going to have basically like active sites on its surface. And so the gases are floating around in the air and they will bind to the active sites on the catalyst. This is known as adsorption, not absorb, absorb. I looked up the difference. Absorb is when something is like soaked into the inner matrix of a material. Adsorb is when it sits on the surface. So the A and B aren't going to go into the middle of the catalyst, they're just going to sit on the surface. So they adsorb onto the catalyst. Now that they're in the same place at the same time, it's easier for A and B to actually react together. So the reaction occurs, we make our product, and then they desorb off and float off again as the product. So, considering this mechanism of action, it makes sense that if you want to increase catalytic activity, you want to increase the surface area of your catalyst. So, powder it instead of having it in a big lump. This Do you have the honeycomb structure of catalytic converters? So you've got support medium with a large surface area and a thin coating of catalyst on the outside. Also, link into this mechanism of action, catalysts can be poisoned by impurities, which kind of similar to the ligand substitution thing we were looking at, they can bond into the active site and then form like a mad strong bond and then not come off again. And then it basically clogs up the active site, poisons your catalyst, and it doesn't work. Example, sulfur impurities poisoning the iron catalyst in the Haber process. Next example, or the next type of catalysis, is homogeneous catalysis. So this is when your catalyst and reactants are in the same physical state. So this is often like, when you do esterification with alcohol, carboxylic acid, and sulfuric acid catalyst, everything's aqueous, it's all in solution. That would be like homogeneous catalyst. And normally a homogeneous catalyst's method of action is, the usual alternative pathway with a lower energy So you form an intermediate species with the help of the catalyst, which is easier than just doing the whole reaction in one go. Most of the time, you see this kind of reflected on reaction profile diagrams. So you could have like, uncatalyzed reaction, catalyzed reaction, or sometimes catalyzed would have two smaller humps instead of one big hump. All right, cool. I feel like we're getting there. How much more paid? How many more? Not that much more. We're doing all right. Autocatalysis. Again, something that I feel like some of you guys kind of have more of a focus on than other exam boards. Autocatalysis, as the name suggests, is when a reaction catalyzes itself. So one of the products of the reaction catalyzes the reaction. So at the beginning, it's going to be mad slow. But once it's started and some product starts to get made, that product then speeds up the reaction and it starts to speed up pretty quickly as it catalyzes itself. Example of autocatalysis is manganese or Mn2 plus auto-catalyzing the reaction between ethane diowate, which is C2O42 minus, and MnO4 minus. So this would be a slow reaction like the other one we saw because they're both negative ions, they'd repel each other. But it would happen eventually. And once it does happen a tiny bit, the product Mn2 plus then catalyzes it and it starts to speed up. So overall, well, it's not overall, but what the sort of first part of the reaction or overall what we're going to get is this. So the MnO4 minus reacting with this thing to make Mn2 plus water and carbon dioxide. But as we said, this is going to be really slow at the beginning because these are both negative ions. But once this happens, the Mn2 plus that's produced can go and react with the MnO4 minus to make Mn3 plus. And then the Mn3 plus goes and reacts with the ethane diowate to go back to being Mn2. So it's doing the exact same thing that I said all transition metal catalysts are doing. Over here, it's 2 plus going to 3 plus. So it's getting oxidized and it's helping this thing to get reduced. And then over here, it goes 3 plus to 2 plus. So it gets reduced and helps that thing to get oxidized. So it always works in the same way. The transition metal's happy to flip-flop between oxidation states, and so it facilitates the oxidation of one thing, then the reduction of another, or the reduction of one thing, then oxidation of the other, therefore sort of returning back to its original way. The only difference with autocatalysis is that this was made as a product of the reaction rather than being added as a separate catalyst. All right, that's fine. Then we get to the final type of reaction that we're going to look at. So, with, as I said, all of the different questions that come up and the different things that happen in the transition metal topic, there are only ever three types of every reaction you see can fit into one of three categories. It's either redox, precipitation, or ligand substitution. The redox ones are the ones like this that we've been looking at with half equations, things change in oxidation state. They're pretty easy to understand. Ligand substitutions we looked at, the main things for us to consider was, are the ligands the same size or is it changing size and therefore going to change shape? And is it going to be reversible or irreversible based on entropy? So the particles and the strength of the bonds, well, the number of particles, yeah, and then the strength of the bonds as well. So if you swap it for something like the hemoglobin, forms a really strong bond, can't send it back again. So we've looked at the first two. The final type of reaction, the precipitation reaction, I feel like is really widely misunderstood. So I'm going to try and explain it so you can understand it. And luckily for us, it's something else that you've learned about before. It's acid base. You already know about this. Hmm. Mm. Coffee splashing on me. Right. This little picture, look at this little picture. This is representing a metal ion with one water ligand. By now, we should know water ligands are small. You can fit 6 of them around the central metal most of the time. I've just drawn one of them. Look at what this water ligand can do. Remember, it's starting off with, it's polar, yeah? So this water ligand can behave as a weak acid and dissociate into a H plus and an OH minus ligand. So water ligands or the metal aqua ions, which is metal complexes dissolved in water, they're acidic, they're slightly acidic. And if you have, let's say, for example, copper sulfate, yeah, copper sulfate crystals, and you go and dissolve that in water, what you end up with are obviously the two ions, and the copper doesn't just stay as copper, it gets surrounded by water. So you end up with the hexa-aqua ions. So all of the ions in solution, your metal ions in solution, end up with water around them, and that's what that colored thing, that's why copper sulfate's blue, because copper with six waters is blue. So when you've got these things dissolved in water and they've got water around them, they're slightly acidic, which means that you can react them with bases and basically do this reaction and turn water ligands into OH minuses. So let's carry on reading. What did I write? Um, right, we already know this. Yeah, metal complexes dissolve in water and get hydrated. Water is a small ligand. You get six of them. It's all octahedral and it's neutral. So as we've said, the solutions with the metal aqua ions are acidic, and I've written an equation. So if you have a metal with six waters around it and it's 2 plus, one of the waters can donate a hydrogen to this water to make H3O plus, so it's acting as an acid, and then that one water will end up as an OH minus, and so you would get one OH minus and then five H2Os. Because you've now got one OH minus with the copper 2 plus, it's now plus one instead of plus two, and you've made a H3O plus because you took this hydrogen off of the water and gave it to the water that was in the solution, not the water ligand. Um, it then says metal 3 plus ions are more acidic than metal 2 plus is. That's because if this was a metal 3 plus, this polar, like the polarness of the water would be more polar, basically, because the electrons are getting sucked really strongly over to the metal because it's a 3 plus ion. So metal 3 pluses are more acidic than metal 2 pluses. And if you have a metal 2 plus or a metal 3 plus, you can basically deprotonate enough of the waters to make it neutral. And when you do that, it forms a precipitate. So that's what I've written over here, showing metal 3 plus going all the way to being a precipitate. So in the first equation, one of the waters gets deprotonated and you go from six waters to five waters and one OH minus. So it takes it from plus three to plus two. In the next equation, another one of the waters is going to get deprotonated, and now you're going to have two OH minuses, four H2Os, and it goes from being plus two to plus one. And then finally, a third OH minus is going to deprotonate, and you end up with OH3, H2O3. Now, because you've got three OH minuses and a metal 3 plus, the whole thing's neutral, you've got a precipitate. If you started with a metal 2 plus, then you just have to do it twice, and then it would become neutral, and then you would get a precipitate. And in these examples, I've shown it, the water ligand dissociating H pluses into the water to get H3O pluses. But I could have also done this if I added, let's see, if I added OH minus instead, then I would get H2O being formed. Oh, I've forgotten the H3O plus here. But you could at the moment I've shown the water ligands dissociating, behaving as weak acids with water, but you could also show a base coming and deprotonating the water ligand. It doesn't have to be like this. So like imagine if I had my metal 2 plus and I've got a water ligand, I could have an OH minus or even like an NH3 coming and taking the hydrogen from here, leaving me with an OH minus and a H2O, or an OH minus and an NH4 plus. But it's not a ligand exchange, it's still deprotonating. So with your precipitation reactions, this is like the second table of colors and things that you have to learn. I've tried again to show the difference between different exam boards and what you need to know and which ones need to know which colors, blah, blah, blah. To understand this is to understand reactivity. So as we said, you can form these precipitates using ammonia or OH minus as well, because ammonia and OH minus will deprotonate the water ligand. So for all of these precipitation reactions, that's what's actually happening. The water ligands are getting deprotonated and turning into OH minuses. And if you do that enough times, you balance out the charge of the metal ion and you get a neutral precipitate. You can take the H's from the H2O either using, like we saw it just dissociating into water. You could use OH minus from sodium hydroxide, or you could use ammonia. Using OH minus from sodium hydroxide is where you get. Do you remember testing for cations? You can test for some metals by adding sodium, you get colored precipitates, or sodium hydroxide, and you get colored precipitates. That's what you're doing. You're forming the metal hydroxide precipitates when you do that reaction. Um, Aluminium hydroxide is a special example. So aluminium hydroxide is known as being amphoteric, which means it can react with acids or with bases. So aluminium hydroxide is when you've got obviously three OH minuses and three H2O ligands. If you add more OH minus, you can deprotonate further and end up with this AlOH4. Or you could add water and basically reprotonate the OH minuses and go back to your hydrated aluminium 3 plus. So just knowing that it can go either way is something you're expected. I think the reason they put this, like, this isn't that difficult to understand, but the key part here is knowing the definition of the word amphoteric. It's like a new term that you have to learn about. Is it always water? When would you mean is it always water? That reacts with the, like, to make it turn into precipitate? No. It might be water. Let me write you out an example of how you could use different things, because that will, I think, help to understand what's really happening. So what is the similarity between all of the equations I'm going to show you? Imagine if I had MH2O6 2 plus, just for argument's sake. That could act like a weak acid. Do you guys know the definition of weak acid? Partially dissociates to give H pluses. So one of the waters is going to turn into an OH minus, so the hydrogen is going to drop off. And now the whole thing's going to be -1, and the hydrogen that dropped off the water is going to float around as a H plus. So I showed that, but instead of having the hydrogen just dropping off and floating around as a H plus, I made it join onto water and turn into a H3O plus instead. But what you could also have would be actually adding a base to pull the H plus off. So I could add OH minus if I wanted to, and then the OH minus would take the hydrogen off of the water for me, and then they would combine to turn into a H2O. Or I could add ammonia, because ammonia is also a base, and then the ammonia would pull the hydrogen off of the water ligand and turn it into an OH minus, and then the ammonia would turn into an NH4 plus. So you can do it with ammonia, you can do it with water, you can do it with OH minus, but it's just always the same thing. The water ligands are deprotonating. I mean, can another molecule act as a weak acid? Which other molecule? With the metal? Would you? I don't know. I don't understand what you mean. The only thing that's acting as a weak acid is water. The water behaves as a weak acid. The water in a precipitation reaction, this is how they work. This is why you end up with precipitates, because the water ligands dissociate and turn into OH minuses. And if you get enough OH minuses, the OH minuses and the charge of the metal ion cancel, it's neutral, and then it's precipitate. If there's other ligands and changes happening to the ligands, that's a different type of reaction. That's ligand substitution. Hopefully that kind of clears it up. Yeah. So as you saw here, all of these different reactions are kind of following the same pattern. Water acting as a weak acid, hydrogens dissociating off, OH minus is getting left behind. And then, as I said, if you start with metal 2 plus, do that twice and you'll have a neutral precipitate. If you start with metal 3 plus, do it three times, you'll have a neutral precipitate. Um, a reaction where there is a bit of a difference between the metal 2 plus and the metal 3 plus is when you add carbonate. So we know that carbonate obviously is a base. And so the acid base reaction that's been happening so far, which is the deprotonation of the water ligand, will continue to happen if you use like metal 3 pluses, because as we said, in a metal 3 plus, again, link it back to physical structure. The charge of the metal ion is stronger, so it pulls the electrons from the water molecule more. The hydrogens are more delta positive, and it's easier for them to dissociate off and for this thing to act as an acid. So if you add carbonates to metal 3 pluses, it just does that same reaction again. The carbonate deprotonates the water and you end up making metal hydroxide precipitates. If you add carbonate to a metal 2 plus, it's not as acidic. And so what you actually end up doing is making metal carbonate instead. So you can see metal 2 plus, which with six waters plus carbonate ends up as MCO3 and water. Whereas if this was metal 3 plus and carbonate, you would end up making MOH3 H2O3 using this acid base reaction, which you already know. This is ionic equation for the reaction of carbonate and acid. You know this, acid and metal carbonate makes salt, carbon dioxide, and water. It's just the ionic version of that equation. So if you were doing this with transition metals, metal 3 pluses, you know that the H pluses are coming from the water ligands that are getting deprotonated by the carbonate because the carbonate is base and the water ligands are acidic. So once you've got your head round understanding these reactions, these are the examples that you see. And the colors, yes, you have to learn them, but understanding what happens is not really that difficult. Everything in this first column, this is where we are, as I said, deprotonating the water ligands with either OH minus or ammonia and turning everything into its neutral hydroxide precipitate. So all of the metal 2 pluses, you need to get two OH minuses. All of the metal 3 pluses, you need to get three OH minuses. So that's what's happening here. All of them turn into precipitates. If you add an excess of OH minus, the aluminium hydroxide precipitate will redissolve because, do you remember we said it's amphoteric? And so when you've got AlOH3 H2O3, you can turn it to AlOH4 if you add more OH minus. So it would redissolve. But the other ones, no change really to them. Here for chromium, you get a change, but not everyone learns that. So again, check your own exam board, check what's going on. For these ones, excess ammonia, no change for most of them because it doesn't do any further acid base reaction. But for some of them, it actually undergoes a ligand substitution. So copper undergoes a partial substitution, and you end up with four ammonias and two waters, really, really deep blue solution. Cobalt, we saw you can swap the water for ammonia and you get this straw-colored yellow-brown solution. And then chromium, you can swap water for ammonia and get something purple. And then finally, the carbonates. Remember what we said, metal 3 pluses are more acidic than metal 2 pluses. So the products of these reactions are just the metal. Oh gosh, what have I done? These are just the metal hydroxide precipitates, the same things that you made over here, because it's the same reaction. Deprotonate the water ligands, get your hydroxide. So that's the same. Metal 2 pluses, not so acidic. So they actually turn into metal carbonates and the waters come off, the carbonate sticks on. So there's theory to this table. It's not just, oh, memorize all of these different things. If you understand the thing that sort of underpins it all, yes, you do sort of have to memorize the colors, which ain't great, but knowing, like, a lot of the time the difficult part of the reaction is, or the questions is knowing what reaction is going to happen when, and you should be able to understand that now that I've given you lot game basically for free. Mm. That's the end of my presentation. Do you guys have questions before I try and look at some questions quickly? Hopefully, as I said right at the beginning, the point here is not for me to baby step you and hold your hand through every single example. It's for me to draw your attention to the places where this topic is just chemistry that you already know about, but reframed and being used to look at these D block elements. So most of it is things that you should understand. Also, I don't expect you guys, just because you listen to me going on for 2 hours, to suddenly be like experts on transition metals. Like now, this doesn't mean go and do questions in exam conditions because you don't know anything yet. Now, maybe watch this again or look back through the notes that I gave you in like this little slideshow thing, keep that open and your book, and then get some questions and spend like it doesn't matter. It might take you an hour to actually figure out what's happened, but if you spend the hour trying to figure out what happened and you actually understand it by the end, it will never take you an hour again. And the next time when something different happens, you'll actually be able to work the answers out. So don't just settle for looking at stuff and being like, oh, okay, yeah, I'll remember that, because you won't. Try and always understand why. Keep asking why. What's the difference? What does this thing look like? What does that thing look like? How many electrons has it got? Blah, 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 blah. That's what it all boils down to at the end. All right. Has anyone got any questions? No. No, no, I don't think so. Mm, 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 mm. I'm like, all right, let me see if I can quickly. I'm not going to sit here and do like loads of exam questions with you lot, but I did open some of the like physics and math tutor exam question packs to quickly like skim over the questions and kind of show you how you're supposed to be relating the information that we've just spoken about to the questions that are going to come up. So this one's pretty straightforward. It's about catalysis. They're asking us about the meaning of heterogeneous catalyst, how it acts as a catalyst, and factors that affect efficiency and lifetime. So this is all pretty straightforward. We know heterogeneous catalysts is when catalyst is in a different physical state. How it acts, it's got the active sites, the things can adsorb, react, desorb, things that would affect efficiency and lifetime if it gets poisoned. So make sure there's no mad impurities, and surface area because of its method of action. Then why is this reaction slow to start with? Oh, they're both negative. How does the iron or whatever it is that iron 2 plus, how does it catalyze it? Well, I know iron 2 can get oxidized to iron 3. So whichever one of those two things gets reduced, react that with the iron 2. And then the iron 3 can get reduced back to iron 2. So whatever thing needs to get oxidized, react that with the iron 3. So the theory I was talking about earlier is all basically just coming back again. It's not really that difficult. Um, then over here, some kind of amount of substance calculation. I'll let you guys figure that out on your own. Some sort of reaction scheme. So look, we've got Fe2 and then we're adding carbonate to it. We should know, as I said, metal 2 plus is less acidic than metal 3 plus is. So if you add carbonate to a metal 2 plus, you will make metal carbonate. So that's going to be metal carbonate, or not metal, iron carbonate. Over here, oh look, air, it's oxidizing the iron 2 to iron 3, and iron or metal 3 pluses are more acidic than metal 2 pluses because the waters are more polarized. So if you react that with metal carbonate, you would make FeOH3, H2O3, neutral, solid, brown precipitate, whereas this would be whatever iron carbonate looks like, which I can't remember off the top of my head. So see what I'm saying? If you understand what's going on, the questions are not very difficult. Give ionic equation for the reaction, that's fine. With Fe3 plus, so that one, the ionic equation there is what I had before. CO3 2 minus plus 2H plus goes to CO2 and H2O. That's what's going on. Why has one of them got a lower pH than the other? Again, the 3 plus, stronger charge, polarizes water more. Um, which one does not show reduction? Quick tip, whenever they ask about these, look for elements. Like I've started with titanium in a compound, so I know its oxidation state's non-zero, and here it's titanium as an element, so it is zero. There's definitely redox happening here. I minus, I zero, definitely redox. Chlorine, chloride, definitely redox. No elements, not redox. Um, So you can see, like, as I said, if you understand everything, answering the questions is not really that difficult. Here, they're asking about contact process, sulfur dioxide, vanadium 5 oxide as the catalyst. So remember, we've got the vanadium 5 oxide that gets oxidized, reduced, whatever, to vanadium 4, and then it gets oxidized, reduced, whatever, back to vanadium 5 again. So when you're looking at the overall reaction of the sulfur oxide, look, it starts as sulfur 4 and ends as sulfur 6. So it wants to get 4 to 6. It's oxidizing it. So oxidize the sulfur, reduce the catalyst, and then oxidize the catalyst back to its original thing again, basically. What else have we got? Iron tablets, fun. More of those kind of like amount of substance type questions. Uh, which would not act as a ligand, whichever one has no lone pair, methane, no lone pair, carbon monoxide lone pair, water lone pair. Because remember, ligand needs to form dative bond. If it doesn't have a lone pair, can't form a dative bond. Work out the charge of cobalt. That's a classic kind of thing. So if the complex balances with a Cl2, the two Cl's are minus, which means the whole complex must be +2. Then ammonia neutral, chlorine -1. So if we got -1 from the chlorine and we want the whole thing to be +2, it means the cobalt must be +3. So you can look at that kind of thing. Coordination number 6. Um, that is not square planar, that's tetrahedral. That's tetrahedral. That's octane. I can't bother to try and picture them in my head. But you can see, I'm just trying to like skim over the questions and show you how what you're being asked relates to all of the chemical understanding that I just gave you. It's not about memorizing all of the examples. It's about trying to understand what's actually happening. Here's another one. What have we got going on here? If you react this with concentrated acid, one of three things is going to happen: either a redox, a ligand substitution, or a precipitation reaction. I know it's not going to be a precipitation reaction because that happens when the water acts as an acid. So acting acid with acid or mixing acid and acid is a no-go. It's not going to be a redox reaction because H pluses and Cl minuses are not going to do redox. So we know that that must be ligand substitution. So we're going to swap the FeH2O6 3 plus for FeCl4 minus. Tetrahedral instead of octahedral. Going that way, because it's a 3 plus, it's really acidic. If I mix it with carbonate, I'm just going to get metal hydroxide. And then down this way, to go from iron 3 plus to iron 2, I know that's a reduction. And then if I mix this and I get the precipitate, concentrated ammonia is going to be ligand substitution or precipitation reaction. So you're going to end up with iron hydroxide. So yeah, more examples, more examples. If you guys don't have any more questions, I'm going to leave it there. What I would like you guys to try and do, if you can, is now that I have given you basically all of the understanding that you're supposed to have, go back and look at questions, but take your time looking at the questions. Don't make it into a test. Keep notes with you, keep books with you, and just try to understand what's going on. One of the things that hopefully will help that you might have noticed that I was doing when I was looking at these questions is like they'll give you a chemical reaction, for example, and then ask you loads of little things about the process, the reaction that's been happening. Try and understand the process in its entirety before you even look at the questions, if that sort of makes sense. So if they talk about some, this and this being mixed together, before you look at what they're asking you, think about what you understand about those two things and how they would react together. If you can understand the whole picture of what's happening, regardless of which little questions they ask you about what's happening, you should be able to work them out. So really try and take your time to actually understand the chemistry here. Don't worry too much about the questions themselves. Try and understand like what is actually happening, because the questions, think about it, the questions are only there to test whether or not you've understood what's going on. So try and understand what's going on and then look at the questions. And obviously in the exam, you've got time limit, you don't have any help, blah, 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 blah. But if you can, like, if you can't understand what's going on with help and no time limit, you're not going to be able to do it quickly off by heart. So yes, it might be a 4 mark question or a 2 mark question, and in the exam you're only supposed to spend 4 minutes on it maximum or whatever. Spend 15 minutes on it now so that you understand it, and then you'll never have to do that again. But if you rush through it and you don't really understand it, oh, I'm just going to remember that, you're not. And then next time when it's a slightly different example, you're not going to get it. So really try and strive for that understanding over anything, because that's the most important thing. All right, I'm finished. You lot can go. If there's any of you that want to ask me questions but you're shy and you want to wait for everyone to leave, I'm going to be the last person to leave. So get out of here if you're finished. I will email this recording to you guys ASAP. And in the top of the chat, I pasted that little slideshow thing that I made as well. So you should have a copy of that. Happy chemistrying. And I might do some more free sessions at some point soon. So make sure that you're following my TikTok so that you can be updated on the other subjects that I'm going to teach about. Mm. Thanks, guys. Thank you for coming. I hope you liked, yeah, found this useful and learned some things from me today. Thank you. Bye. Oh, that was fun. I was actually very excited to do this, you know. I'm so neaky. I love chemistry so much. Like, I find it very, very fun to talk about. I'll do this all day. Thanks, guys. Bye bye. You leaving? Question? All right, cool.